Solving general chemistry problems. Electrochemistry. In any electrical circuit, and an electrochemical cell is just such a circuit, there are various performance variables that can be measured. The resistance is given by the variable R and is measured in ohms. The total circuit resistance is made up of resistance from each of the parts. We can measure the whole circuit or just part of it as needed. The current that flows is given the variable I and is measured in amperes or amps. The current in a circuit is the same everywhere. A current measurement at one point asserts that the same current is flowing at any other point. The potential difference, or voltage, is given the variable V and is measured in volts, which also has V as the unit symbol. The voltage is really a voltage or potential difference between 2 points in the circuit. Every part of a circuit, even the wires making connections, have some kind of voltage difference or voltage drop. One generally tries to design circuits so that an important element has the majority of the voltage drop across it. In an electrochemical cell, we tend to ignore the potential drop inside the cell, the drop through the electrolyte solutions and through the salt bridge, for instance, and attribute the cell potential as that measured between the two electrodes. A voltmeter is what is known as a high impedance device. It means that its internal resistance is very large, especially compared to other components in the circuit. As such, it draws extremely little current itself and provides an accurate voltage reading. When we measure the voltage of an electrochemical cell, we draw a vanishingly small current from it and obtain an accurate voltage reading. The cell does not change much because the current drawn is so small. But when we want to use an electrochemical cell to do something useful, run a toy, electroplate a tool, etc., we need to provide a load to the circuit that allows a current to flow. If the load has a small resistance, a large current will flow. If the resistance is large, the current will be smaller. The voltmeter can remain in parallel with the load because of its huge internal resistance, which is generally many orders of magnitude larger than that of the load. The voltmeter doesn't disturb the circuit and is, as in this picture, measuring the voltage drop across the load. If the internal resistance of the cell is small by comparison, then the voltage can also be attributed to the cell. We measure that current with an ammeter placed into the circuit. An ammeter is a low impedance device, meaning that it has very little resistance and does not add appreciably to the current being drawn. With a voltmeter across the electrodes of a cell and an ammeter anywhere in the external circuit, these devices can together measure the voltage and current in the cell and provide the information we need about it. A fourth property is that of power, the rate at which work is being done. The symbol P is used for power and it has the unit of watt. The unit symbol is capital W. The first of two important equations for these relations is Ohm's law, which is that V is equal to I times R. You may even hear people refer to the voltage drop across a circuit element as the IR drop. It means the same thing. The equation for power is P equals I times V. With reorganizing Ohm's law and substituting, P is also equal to I squared R or V squared over R. Depending upon the kind of information that you have at hand, which version you choose to use. So it is easy to set up a cell, whether galvanic or electrolytic, and measure voltage and current. Michael Faraday was one of the great experimental scientists of the 19th century, and much of his work revolved around electrochemistry. His body of work is tremendous, but we want to focus on one feature especially important for electrolysis. He observed and was able to quantify that the amount of material that was produced in an electrolysis cell, whether a solid, liquid, or a gas, was directly proportional to the amount of electric charge that flowed through it. By measuring the current and recording the time, he was able to make this connection. Now bear in mind that this was before the electron was discovered and was even before the periodic table of Mendeleev. We now understand how the number of electrons transferred in a reaction must be directly connected to the amount of material consumed or produced through the stoichiometric relationship of the balanced chemical equation. So how do we measure charge? Well, we do so by measuring current. The total charge transferred is the integral of the current over time. In general chemistry, we deal with problems wherein the current is constant, so that we have the straightforward relationship charge Q is equal to current times time. If current is in amps and time in seconds, then charge is measured in coulombs. Now we also know how charge is related to the number of electrons. The Faraday constant, named after him of course, connects the two. Charge Q is equal to N, the amount of electrons measured in moles, times the Faraday constant. F has the value 96,485.33289 coulombs per mole, and it's usually just rounded to 96,485. When we have measured a current for a certain length of time, we can relate that to the amount of electrons that have flowed through the electrochemical circuit. We equate the two expressions above, for they both relate to the charge Q that is transferred. Then by rearranging the equation, we can solve for N, the moles of electrons, which equals current I times the time, in seconds remember, divided by F. From here, with a balanced chemical equation, we can determine the moles of any of the reaction participants. We just need to know the reaction relationship between electrons and the species of interest. Then once we know the moles of a substance, we can, knowing its molar mass, find that mass of material involved, or if it is a gas, using the ideal gas law to determine the volume involved. Here is an example. In a copper electrowinning operation, each electrode has 130 kilograms of copper deposited on it in exactly 6 days of operation. What is the current that must have been flowing for the entire length of time? We need to find the total charge that must have flowed and the time. With that, we can find the current. First of all, the time. How many seconds are there in 6 days? 6 days times 24 hours per day times 60 minutes per hour times 60 seconds per minute for 518,400 seconds in 6 days. We know the mass of copper deposited, but we need moles. Use the molar mass to convert. We look it up as 63.546 grams per mole. So the moles of copper is 130,000 grams divided by 63.546 grams per mole, which equals 2,045.76 moles of copper deposited. So how do we find moles of electrons? Well, we look up the standard reduction potential tables for this copper. We find this relationship. Now, because the valence of copper is +2, it takes 2 electrons to reduce 1 copper ion to a metallic copper atom. The number of electrons must be twice the number of copper atoms deposited. Therefore, the amount of electrons is 4,091.52 moles. What is the charge in coulombs associated with this number of electrons? Bring in Faraday's constant. Almost 395 million coulombs of charge was passed to deposit all of this copper. What was the current that was needed to be able to deliver all that charge in a 6-day period? We find I is equal to Q over T, which gives us 761.5 amps. And that is a pretty hefty current that has to be delivered for the entire 6 days. Here is another example. Set up an electrolysis cell with 2 platinum electrodes. In the cathode cell, place a 1 molar solution of silver nitrate. In the anode cell, have a 1 molar solution of sulfuric acid. Apply a sufficient voltage to drive the electrolysis. Have it on for 3.5 hours. The platinum cathode weighed 22.3842 grams before electrolysis, and it weighed 23.2974 grams afterwards. The platinum anode weighed the same before and after. A gas bubbles off the anode and is collected. What are the half reactions at each electrode? What must have been the current, and assume it was constant throughout? What is the gas? What volume does it occupy at 22 degrees Celsius and 100.5 kilopascals? Assume it's been dried and the water vapor removed. We know which electrode is the cathode because we connect the negative terminal of our power supply to it. Silver must have been deposited at the cathode. Its mass must be 0.9132 grams. The molar mass of silver is found from tables to be 107.87 grams per mole, so the amount of silver deposited then is 8.466 millimoles. The reaction occurring at the cathode must be the reduction of silver. Any other possible reactions, the reduction of nitrate or the reduction of water, do not produce solid products, only gaseous ones. We can't say more without knowing any relevant overpotentials, but we do not need to know any more since a solid is deposited and it could only be silver. The cathode reaction is this. Now at the anode, sulfate ion and water are potential reactants for oxidation. The SRP for sulfate is plus 2.01 volts, while that for water is plus 1.23 volts. Without being asked to consider any overpotentials, the water reaction will occur first, as it has the least positive SRP, so the relevant reaction is this. Now I've written it as an oxidation. Notice that oxygen gas is being produced at the anode. Remember that for the anode reaction, you look through the SRP tables for a reaction with the species of interest on the product side, so when switched around to be an oxidation, it will be on the reactant side. To find the current that must have been flowing, first determine the time involved in seconds. Multiply through to find that 3.5 hours equals 12,600 seconds. Next, what charge had to be transferred to reduce all of that silver? The stoichiometry, and now look at the cathode reaction equation, between the silver and the electrons is 1:1. So the amount of electrons must also be 8.466 times 10 to the minus 3 moles. And what is the amount of charge in coulombs represented by these electrons? Use the Faraday constant. It's 816.8 coulombs. And what current would be needed to deliver this charge for the 3.5 hours? Well, remember that Q is equal to I times T, so that I is equal to Q over T, and it is just about 65 milliamps of current. Now for the last part. What is the gas? Well, clearly from the half reaction, it is oxygen. How much of it has been formed? Well, we know that 8.5 millimoles of electrons were transferred at the cathode, and the exact same amount must also pass through the anode. The current must be the same throughout the circuit. However, the stoichiometry for this reaction is not 1:1. Rather, it is 4:1. It takes 4 electrons to produce 1 molecule of oxygen. So the amount of oxygen produced is about 2.12 millimoles. What volume would the gas occupy at the given temperature and pressure? Use the ideal gas law. Be sure to convert temperature to Kelvin. 22 degrees Celsius equals 295 Kelvin. And get R and P into the appropriate units. Recall that 100 kilopascals is equal to 1 bar, so the pressure here is 1.005 bar. Then we can use R in units of liter bars per Kelvin mole. Substitute in to get 51.6 milliliters of oxygen gas is collected. Now there are a lot of equations and numbers on this page. Look again at the questions asked. Here are the answers that we needed. First, the reactions that are occurring at each electrode. Then, the current that must have flowed to deposit that silver. And finally, what is the gas and the volume it occupies under the given conditions of temperature and pressure. So here's one more problem, and it's quite challenging. I'll give you the question and then a little hint on how to approach the solution. Then I suggest you pause the video and take a crack at it yourself before looking over the solution. Give a good effort first, then continue on to it. Here it is. A solution contains the sulfate salts of cadmium and indium. The solution is electrolyzed until all of the metal is removed from solution. Which metal plates out first? The electrolysis is complete after a constant current of 900 milliamps is passed through the cell for 2.5 hours. The total mass of metal deposited is 4 grams. What is the mass percent of cadmium in the product? Now the hint is to notice that you have 2 significant pieces of information, the total mass deposited and the total charge passed through the cell. You also have 2 unknowns, the mass of cadmium and the mass of indium. In solving problems in general, one thing to always look for is that you have enough information. When you have as many equations as you have unknowns, then you are able to solve the problem. Try to write out an equation for the total mass in terms of the contributing parts. Write out another equation for the total charge in terms of the same contributing parts. Substitute one into the other and see if you can isolate for one of the unknowns. Okay, now is the time to see if you have some problem-solving skills. Okay, hopefully you got an answer. Let's take a look at my solution. Here's a question restated to remind you. And first of all, I want to round up the data that we will need. We need to relate atomic mass to the atomic amount, so we'll need the molar mass of both species. We also need the half reaction equations for the two cathodic processes. We looked them up in tables, and they are here. Now notice that it takes 3 electrons to form one indium atom, while it only takes 2 electrons to form a cadmium atom. These two relationships are critical in our solution to the problem. We will use them presently. Now the cathodic reaction that is least negative will occur first. The indium will start to plate out first. The two potentials are quite close, so the separation between the two may not be perfect. At some point, as the indium concentration decreases, they may be starting to plate out together. Now, the more challenging part of the problem, we need a couple of expressions that can be used together to solve for the two unknown portions. The first relation to look at is the mass. The 4 grams of metal consists partially of cadmium and part indium. We know that the electrical information will be related to moles of material, so we need to recast this in terms of moles also. The molar mass makes the connection. Now this is our first relation, which involves the as yet unknown amounts of the two elements. The other relationship is that of the electrical measurement, the current operating for 2.5 hours. The charge is both the current times the time in seconds, and it is also the number of electrons in moles times the Faraday constant. Convert 2.5 hours into seconds, you'll find it is 9,000 seconds. Convert the milliamps into amps, it's 0.9 amps. The total amount of electrons that have been transferred is 0.08395 moles. Now this total amount of electrons is apportioned in an as yet unknown way between the two elements. Some portion of the electrons were used to convert cadmium atoms, and the other portion converted the indium atoms. But we need to relate these to the amount of atoms deposited. Remember the stoichiometric relationship between electrons and each element? 2 electrons for each cadmium and 3 electrons for each indium atom. The sum is the total number of electrons, which is the 0.08395 moles found above. This is the other equation. Put together with the mass equation, we can solve for the two unknowns. The approach one takes is to rewrite one equation to solve for one of the unknowns, and then substitute that into the other equation, which eliminates one of the unknowns. We now solve for the remaining unknown, and we should only need constants that we know. Solved. So now you can tackle this in many ways. My approach here is to solve the electrical equation for the moles of indium. When rewritten, we get this. Now we go back to the mass equation and substitute for the amount of indium. And for clarity, let's just expand out that second term. The only unknown in this equation is the moles of cadmium. Move the terms around to get the amount of cadmium variable on the same side and factor it out by itself. Now make sure that you see what I have done in this step. Pause the video if you need time to review it. Make sure that this arithmetic doesn't cause you difficulty. Okay, let's continue. Divide that term that remains multiplied to the amount of cadmium of the cadmium variable, and you have the final equation that can be solved for the unknown moles of cadmium. We substitute in for the 2 molar masses and the total amount of electrons, along with the measured mass of the deposit, and we find that the amount of cadmium deposited is 22.1 millimoles. We multiply this by the molar mass of cadmium to find the mass of cadmium to be 2.48 grams, and 2.48 grams is 62% of the total mass, and the question has been answered.